M dot equals to rho Q. And Q is volume divided by time. M dot here. Yeah, that's M dot. That's flow rate, which is equal to mass over time, which is equal to rho AB, which is equal to rho Q, and Q is volume over time. Hey, they're all in your lecture notes. They're all in your lecture notes. I am not recreating anything. So example, if this kind of question does come out, it will be under MCQ. Because it's simply punching calculator get the answer. And in exams, right, out of the 20, I think it's 20 MCQ. If I do have calculation, it will be very simple calculation, just one step. That I can assure you. MCQ, I like to test you on your understanding of concept rather than calculation. Okay, so continuity equation is A1B1 equals to A2B2. Yeah? Continuity equation. Underline conservation of mass. And then the formula, you don't need to memorize formula will be given. So underline conservation of mass. Next. Okay, this you already know. I think you don't even need to underline. By applying continuity, you will know when area decrease, volume increase. If you forget, then think of the nozzle. Okay. Manuri. Nothing. There isn't much I need to highlight. So Manuri is conservation of energy. Another common MCQ question. Conservation of energy. So circle energy. Okay. This one nothing much to mention. Besides applying Manuri. What is the standard 5 steps? Yeah, what's the SOP for? Yeah?
Look left, look right. Left again.
Here. First step, identify 2 points. I think in my exam I have already identified the 2 points. So you don't have to worry too much. Apply Manuri to the 2 points. Identify common terms. Identify zero terms. Solve. So if we were to use this as an example, the 2 points identified already. Okay, so you apply Manuri to these 2 points. That's what you have. Common terms, they are both exposed to atmosphere. So P1 equals to P2 equals to PATM. You can just cross it out. And then think of the reservoir. Here the velocity will be equal to 0. So you have identified common terms, identified zero terms, and then you solve. Am I too fast?
Yes.
Yes, this is the second, third time, fourth time. Okay, continue, same here. The important thing for you to note is to be able to identify that these 2 points. If they are open to atmosphere, then it should be PATM. And then the surface is always zero velocity. We talked about Z1, Z2. I think some of you had some confusion on Z1, Z2. So if we go back to this example here, if this is point 1 and that's point 2, so this will be Z1, Z2. So I have indicated Z2 as 0. What does that mean? Where's my datum? Below. So my datum is, I have fixed my datum on this line here. When I fix my datum here, means Z2 equals to 0. If I were to fix my datum here,
Minus.
Z1.
Minus.
If I repeat my question, if I fix my datum here, what will be Z1?
Minus. Negative.
Z1. Where's 1? What is here?
Oh.
Sorry? 0, yes. And then what will be Z2? Minus 5.
Minus 5.
Yeah. And there is no right, no wrong, you know. If you fix your reference here, you are going to indicate this as 0, this as minus 5. To rearrange, you will still get the same answer. If you don't believe me, why don't you try it out? Put this as 0, put this as minus 5, and then after that you're going to bring this V2 over, or you bring this over, you will get the same answer. It's exactly the same one. So there is no fixed rule where you should fix the datum. But my guideline, my advice to you is always try to have the datum at the lowest level, so that you don't need to work with negative numbers. Because when you see negative numbers, you tend to get a little bit frightened. Okay? Same here. If I fix my datum at point 2, then Z2 will be 0, Z1 will be 10 meters. Okay? And I went through review the different forms of maneuvering. I introduced to you static pressure, dynamic pressure, hydrostatic pressure, and then total pressure. So if I were to add these three up together, then we would have what we have. Then we would have total pressure. But when we are dealing with air, this hydrostatic pressure will not be applicable. So in the end, when I pass around the pitot-static tube, you remember the pitot-static tube? Remember, the front hole measures the total pressure here, which is the sum of static plus dynamic. Stagnation point. Can you underline, or can you write somewhere stagnation point V is equal to 0? Common MCQ question. So, stagnation, again? I've said again already. Stagnation point, the velocity is 0. So you can just put V is equal to 0 somewhere. Just to remind yourself. Continue?
Yes.
Yeah, so this is, we have already gone through, only thing that I want to highlight is, pitot tube and pitot-static tube, they are two different equipment. Pitot only measures total, pitot-static measures total and static pressure. Okay, continue. We had this example, I don't want to go through. Okay, but in case you cannot recall why we still use this formula, which is a chapter 2 formula, H rho G, is because I have a manometer here. So with the height, I can find the pressure. Okay. MCQ question. Hydraulic grade line and energy grade line. Energy grade line is all these three terms add together. Okay, I should have it here. Energy grade line, pressure head, velocity head, elevation head. And hydraulic grade line, pressure head, elevation head. Common MCQ question. So all you have to remember, if you don't want to memorize so many things, at least remember that the energy grade line is always higher than the hydraulic grade line. Because why? There is a velocity term here. Okay. Thank you. EGL is always higher than HGL because there's a velocity head here. That's topic 3. So then if we go to topic 4, just wondering whether I can just go through the summary.
Tengah rekod dari tadi.
Why do I just go through the summary for topic 4? Well, you already have this in your whole book, right? Wow. Okay, topic 4 already? Yeah? Know the difference between laminar and turbulent flow. Laminar, layer by layer. Turbulent, what is the word to describe turbulent flow? Alphabet M.
Motion.
Yeah, there's mixing.
Mixing motion.
Okay, so you can see there's mixing, and then here is layer by layer. Laminar boundary, so Reynolds number definition RIV. So when I have high Reynolds number, means this force is nominal. When I have low Reynolds number, it means the viscous force is nominal. Remember the video that I showed you? The 3 color, then the turn
Reverse.
5 rounds,
Yeah.
you mix, and then after that they reverse, and then you went back. That was a low Reynolds number flow. When the Reynolds number is low, viscosity is very, very high. In other words, when the viscosity is very high, they don't mix. So this is the internal resistance that they have. You will also then introduce kinematic viscosity. No, this is the topic 1 you have it. Kinematic and dynamic viscosity. 2300, critical Reynolds number. Yeah, 2300 is the critical Reynolds number. So if you want, circle 2300, that's the critical Reynolds number. Okay. After that, we look into the velocity distribution. We did some calculation. Now, you don't have to worry this formula. You don't have to worry this formula. Why? Okay. For the same question, although you can, if you can memorize, of course you can try to memorize and solve the question. Otherwise, the default is always you have Reynolds number equals to rho V D over mu. This is your absolute viscosity. Or you have Vd over mu. This is your kinematic. Now, if you are given m dot, how do you find velocity? Can you find velocity from m dot? What's the formula that I asked you to underline just now? Rho A V. So if the question gives you m dot and you are required to calculate Reynolds number, use this formula, find V. If the question gives you flow rate, this is flow rate is equal to A times V, we'll find V. Once you found V, depending on whether you are given absolute or kinematic, then you choose the formula. Calculate the Reynolds number. Okay? So if you are planning to do revision and you see this big formula and you don't see it in a formula sheet, please don't panic because you already know these two formulas. You can calculate. And then we went through some calculations for head loss. So I brought in a pipe and I say if I were to blow air 10 meters per second, it will come out less than 10 meters per second. If the air going in is 10 pascal, it will come out less than 10 pascal because of frictional loss. You can calculate the frictional loss using this formula. Okay, what is F? Friction factor. So if you can remember the frictional loss, what's another name for frictional loss? Frictional head loss.
HF.
Anyone remember? Major or minor?
Minor.
Remember the HL total is equals to H. Oh, forgot. Internal flow. What is HL total equals to? What is HL total equals to? Can you see this? What is this? Okay. The total head loss in a pipeline is the major loss plus the minor loss. What is major loss? Major loss is equal to your frictional loss, which is equal to FL over D, V square over 2G. F is your friction factor, and if it's laminar, F will be equal to 64 over RV. Now all these are, we have already gone through in our lectures and you already had your tutorial. If it's turbulent, then you read off from, anyone? What chart do you read off from? Moody chart. So you read off from Moody's chart. You probably already, you should have some practice during your tutorial. But in exam, I don't expect you to read off from Moody's chart. So if it's turbulent flow, I will give you the value of friction factor. But if it's laminar flow, then I'm expecting you to apply this formula and calculate friction factor. Okay? Minor loss is all the bands. Remember I brought in the band type? So once you have bands, you have valves, you have sharp exit, then this loss here is going to be summation. You sum out all the KL. What is the name of KL? What is KL known as? Hello, can you remember what does KL represents?
Minor loss.
Loss coefficient. Okay? So if you have 3 bands, 1 valve, 2 sharp exit, 1 sharp exit, 1 sharp entrance, then you add up all the loss coefficient, add them all up, you should get the HL total. So in other words, if I have this band pipe, just a simple band pipe, flow goes in here, comes out here. As it goes through this band pipe, there's going to be major loss, there's going to be minor loss. Can you understand?
Yeah.
Now, you understood as well that there will be a pressure loss. The pressure loss, which is represented as delta PL, all you have to do is, once you have found out what is HL total, it simply equals to HL total times rho times G. That's it. And this is the formula that you have done in topic 2. Okay, so we have gone through all this, we went through the calculation. Something that I wanted to remind you is parabola. Where's the parabola? Remember laminar flow, what's the shape of the parabolic? Okay, so there's a parabolic and then there's a turbulent one. Parabolic, okay, this has already been underlined for you, so you don't need MCQ, common MCQ question. Laminar flow is parabolic and then turbulent is fuller. We went through this, I'm not going to go through this video. Okay? But one question came out a few times for Moody chart under MCQ. So I highlighted to you, right? If you look at this Moody chart, to the right of this dotted, can you see this dotted curve? To the right of it, the line is almost constant. In other words, it is independent of the Reynolds number. Whether your Reynolds number is here or here, you will read off the same F value. So we say when the flow is fully rough, turbulent, it is independent of Reynolds number. This was one of the past year MCQ exam questions. Okay? As long as it's on the right hand side of this dotted line, you will have a fully rough turbulent flow, and when that happens, it is independent of Reynolds number. Continue. I don't need all this. And minor loss. Okay. Minor loss we went through already. Okay. This one here. Remember this? This was example 7. So in example 7, we were supposed to calculate the total head loss. Total head loss is simply equals to the major loss plus the minor loss. So you just have to do all the substitution. And then I continue to ask, what is Z1? So in order for you to find Z1, you will need to apply manually, 0.1, 0.2. Then you will realize, right, P1 is the same as P2, which is PAPM. B1 equals to B2, which is equal to 0. Now you realize that once you understood the concept that I have tried to share with you, you practically can solve all types of Moody questions. Because you already know that you have identified 2 points, you already knew that there are common pressure terms, there are 0 terms. Cancel, just solve it. It is as standard as your SOP when you carry out maintenance work. Okay? That's all topic 5. Actually, aren't you like tired of hearing me repeating so many times? That's right. Then how come you still want me to repeat? Okay, now external flow. Now extra information. Now external flow, there are only 2 formulas, the drag coefficient and the drag force and the lead force. it's more, there are probably 3 MCQ questions for this topic, and they circles around boundary layer, flow separation, mainly boundary layer and flow separation. So in this case here, I taught you about the boundary layer. I told you the no slip condition. Remember the no slip condition?
Mm-hmm.
Okay. You can circle this no slip condition. Because when the flow goes very near to a surface, it is not able to slip. It will just get stuck. And when it gets stuck, the velocity equals to 0. So I put here, no slip condition means the flow comes to a complete stop. Can find?
Yes.
Yes,
Okay.
just now the Kahoot question. Outside the boundary layer, the frictional effects are negligible. So the flow is considered implicit, that means no friction. Another word for it is ideal.
I did.
Transition point. So from laminar to turbulent.
Oh, transition point. Okay, correct.
And I was trying very hard 2 weeks ago to explain to you the difference between laminar and turbulent boundary layer. I went through all this with you, and I told you that the velocity is low for laminar boundary layer, is high for turbulent. Let's go back to this slide. So if this is a distance away from the wall, from the surface, from the surface. So for the same distance, if you have a laminar boundary layer, the velocity is only this much. If you have a turbulent boundary layer, the velocity will be higher. Remember we talked about the golf ball? Did we talk about the golf ball?
Yes.
Yes? And I told you that golf balls, the dimples are there to make the flow turns from laminar to turbulent.
Turbulence.
Once you have turbulent flow, it has got higher energy level. What does that mean?
Further.
Further.
It delay or it fasten separation.
Fast.
It delay
Faster.
separation. When it delays separation, what happens to the wake?
Right.
Bigger or smaller?
Smaller.
Bigger. Bigger.
Luckily, I still have all these.
Bigger. Bigger.
Okay, so you see, I was trying to tell you for the same distance away from the surface, if it's laminar, the velocity could be, let's say if this is 10 meters per second, this probably can be 9 meters per second. This is probably about 3 meters per second. So, laminar boundary layer, lower energy level. Turbulent boundary layer, higher energy level. Then I see I know how to wake. Remember this? Smaller wake is formed when the separation is delayed. Bigger wake is formed when your separation is early. Why do the flow separate early? Because it has got a lower energy level. Because it is laminar. Laminar means lower energy level, it will separate early. Separate later because turbulent boundary layer has got a higher energy level. Okay, common MCQ question. So, smaller wake, lower drag, the golf ball will fly further with the same swing force. Continue. Okay, separation point we've gone through, golf ball we've gone through, and then skin friction, we don't care about this. Skin friction, drag and form drag. Skin friction, drag and form drag, can you remember this? Form, the word form has the same meaning as shape. That means the drag is due to the shape. MCQ question again. So calculation wise is straightforward. This is the first formula that you need to know, drag. Okay. The critical Reynolds number by external flow, Kahoot question, 5 times 10 to the power 5. Some of you gave me 3,000. 3,000 is more for internal flow.
3,000 is.
And then with calculation,
3,000.
go through this. I highlighted to you about the area. When you are asked to calculate the area acting on the object, if the flow is coming in this way, sorry, I will use you as a viewer. If the flow is coming in this way, then the area that we use is going to be this length multiplied by the diameter of this pole. Let's say it's a pole or a log in the river. If the flow is coming in this way, okay, then the area here is going to be the cross-sectional area, pi r squared. This will be just length times diameter. Okay, so you always ask yourself, hey, which area is the flow impinging on? Then you use it as the area. Otherwise, this is straightforward. Streamlining, we talk about streamlining. And then we talk about leaf. That's the formula. I drew the whole question just now. Leaf is perpendicular. Remember this? Remember this? No.
Lift.
Leaf.
This diagram here, I drew to illustrate to you or to highlight to you that if my flow is coming in this direction, my leaf is always perpendicular to the flow direction. My drag will always be parallel. If my flow is coming in this way, then this will be my drag, this will be my leaf. MCQ question. So just remember, perpendicular to wind or to the flow direction. MCQ question. Otherwise, not much that I want to run through. Streamlining is just to reduce drag. MCQ question again. Streamlining is to change the shape of an object. Shape of object just to reduce drag. I'm done for 3 topics. Today's topic, only 2 formulas. So what are the 2 formulas? First formula, second formula. Formula 1 looks easy. Does that look easy? Should be easy. In fact, if you actually allow me to rush through, I can finish this topic in half an hour. But no, I'm not. Just look at this. What's the opposite of compressible flow?
Expand. Expansion flow. Compress.
Compress is the pushing.
I don't think I need to give you this. So I will. In fact, let's see how much time we have learned in topic 1. Opposite of compressible flow is incompressible. When a flow is compressible, what does it mean? Or when a flow is incompressible, what does it mean? What remains constant if it's incompressible?
The distance.
You have this at your fingertips. Incompressible flow means what?
Density.
Density, very good. Density equals to a constant. When it's compressible, I'm handicapped. I tell my full-time student when you speak, I can't speak because I want to give you my respect. Yeah, sorry. So I'll wait for you, then I'll. Okay. When we have compressible flow, the density is no longer a constant. Now, do you not agree that air is compressible? Yeah?
Yeah.
Yes. So when do we know that the calculation requires us to treat the flow as compressible? When do we treat the flow as incompressible flow? How do we know?
When you
If I was throwing you a question,
somewhere.
then you'll be like scratching your head. So is this compressible flow or incompressible flow? If we are dealing with